All right, we'll start off with problem number 1, and that is find the derivative of the inverse trigonometric function. Y is equal to the inverse sine of 4x to the fifth. All right, in this case, this is going to be one of those use substitution. We have to use the chain rule, okay? Because the inside function is a differentiable function. So we deal with the inverse sine, and its derivative is going to be, in this case, 1 over the square root of 1 minus u squared times du dx. Okay? So, if I do dy dx, or y prime, I could use that notation if I wanted to. That's going to be 1 over the square root of 1 minus, and what's inside the parentheses, which is at 4x minus 5, that will have to be squared. And then that's going to be multiplied by the derivative of what's inside the parentheses. The derivative of 4x to the fifth would be 20x to the fourth. And then if I simplify this a bit, I'll put that 20x to the fourth in the numerator, and that's divided by the square root of 1 minus. Now I need to square the 4x to the fifth. Let's see, 4 squared, that's 16. And then if I raise a power to a power, we multiply the exponent, so we bring the x over and multiply 5 times 2, that would be 10. And I would go no further than that. So the derivative of the inverse sine of 4x to the fifth will be 20x to the fourth divided by the square root of 1 minus 16, x to the 10th. Okay. Are there any questions about problem number 1? And this is from section 3.10, dealing with the inverse trig functions. All right, number 2 is from section 3.11, dealing with related rates. And that's this: a spherical balloon is inflating with helium at a rate of 72 pi. Yes?
Will you give us the formulas of the shapes?
Yeah, I can do that, yeah. Okay. Any other questions? Okay. It's this: a spherical balloon is inflating with helium at a rate of 72 pi cubic feet per minute. How fast is the balloon's radius increasing at the instant the radius is 3 feet? Okay, so let's see here. We have a rate of 72 pi cubic feet per minute. So in this case, we're dealing with a change in the volume with respect to time. So that's dV dt. That's equal to 72 pi cubic feet per minute. So that's given to us. And also, we're looking at, we're trying to find how fast is the balloon's radius increasing, which is actually going to be the change in the radius. So that's dr dt is what we're looking for. And this is at the instant the radius is 3 feet. So we know what r is. That's 3 feet. And the formula for the volume of a sphere is this: 4/3 pi times the radius cubed. 4/3 pi times the radius cubed. That is the volume of a sphere. Okay. So what we need to do here is take the derivative of each of these variables with respect to time. Okay. So the v, its derivative will be dv dt. And that's equal to 4/3 and pi are constant, so we'll bring that over. The derivative of r cubed would be
r squared.
3r squared. Bring the power down, rewrite the variable to the 1 less power. And we can divide out those 3's, as you can see here. So that means dv dt is equal to 4 pi r squared when we simplify it.
Also dr dt, right?
Okay, yeah. This needs to be dr dt as well. Okay, because we're taking the derivative of each variable with respect to time. Okay, so now let's do some substitution here. All right, that dv dt is given to be 72 pi cubic feet per minute. So I'm just going to say this is 72 pi, and it's equal to 4 pi times the radius, that's 3 feet. So it'd be 3 squared times dr dt. Then if I simplify this, 72 pi is equal to, let's see here, if I square that 3, that's 3 times 3, that's 9, times the 4 in front would be 36. So it'll be 36 pi dr dt. And then next, to get dr dt by itself, we divide both sides by 36 pi. So that means dr dt, here the pi's divide out. 72 divided by 36 will be 2. And in this case, this is a rate. That means it's going to be in feet per minute. Because our units is in feet, the time is in minutes. So in this case, the balloon's radius is increasing at a rate of 2 feet per minute, the instant that radius is 3 feet. Okay. Are there any questions about problem number 2? Okay, does everyone have this? Okay. All right, problem number 3. In this case, there are 10 parts to this. Okay, and this pretty much covers stuff from section 4.1, then 4.3. Yeah, 4.1 and 4.3. And that's this. You're given the function f of x equal to x cubed minus 6x squared plus 9x. And here we're going to be using that to find the following. Okay. So number 3 is going to be that f of x equals to x cubed minus 6x squared plus 9x. All right, so the first part is just finding the first derivative. Okay. So the first derivative would just be f prime of x. So what would be the derivative of x cubed minus 6x squared plus 9x? What would that be?
3x squared.
Okay.
And then 12x plus 9.
Okay. So that's part A, just finding that first derivative. And then part B is finding the second derivative. So here f prime of x was 3x squared minus 12x plus 9. So f double prime of x, or the second derivative, will be what?
6x minus 12.
6x minus 12. Okay, so parts A and B are just finding the first and the second derivative. Part C is identifying your critical points. All right, so when we find out critical points, we take the first derivative, f prime of x, set that equal to 0, and solve for x. So our f prime of x was 3x squared minus 12x plus 9. That's equal to 0. All right, let's see here. What can we factor out in 3x squared minus 12x plus 9?
3.
Let's factor out the 3. So that means I'm going to have, let's see, x squared minus 12x divided by 3. That's 4x plus 3 equal to 0. Bless you. Let's see if we can factor that x squared minus 4x plus 3 into two binomials here. So that means the x squared breaks up as x and x. The middle term is a minus and the last term is a plus, so I need minus signs here. What factors of 3 would give me a minus 4x?
Minus 3 and minus 1.
Right. So here I get 3 times x minus 3 times x minus 1 equal to 0. And then from here we just set each individual factor equal to 0. So I'm going to set 3 equal to 0, set x minus 3 equal to 0, and x minus 1 equal to 0. And then solve for x. Well, 3 equal to 0, we can eliminate that since that's a false statement. For the x minus 3 equals 1, what must x have to be equal to? 3. And then for x minus 1 equals 0, x must be equal to 1. So these are your two critical points. X equals 3 and x is equal to 1. Now part D is to identify inflection points or possible inflection points. That's where we set f double prime of x equal to 0. And f double prime of x from part B is that 6x minus 12 is equal to 0. And then we solve this equation for x, so if I add 12, that means 6x is equal to 12. Then divide both sides by 6, you'll get x is equal to 2. So here, my possible point of inflection would be at x is equal to 2. Okay, now part E is this. On what intervals are the function increasing? And also part F is on what intervals are the function decreasing? So pretty much, this goes back to part C where we had to find out critical points. And to do that, let's see. I'm going to say here this is increasing on. And then for part F, it's going to be decreasing on because that number line is what's going to help me determine the intervals on which the graph of that function will be increasing and decreasing. So if I put those critical numbers on a number line like this, let's say 1 is here, I'm going to put 3 over here because those are my critical values. And that separates this interval into, the number line into 3 intervals. One of them will be from negative infinity up to 1. The next one will be from 1 to 3, and then from 3 on to infinity. And then for each one of these, we're going to pick a test point and use that f prime of x derivative to determine whether it's positive or negative. So I'm going to test for negative infinity to 1. Let's use x equals 0. And then substitute f prime of 0. Let's substitute 0 into the f prime of x function, which is up here. So if x is 0, that means I'm going to have 0 plus minus 0, that's going to be 0 plus 9, which is 9, which is going to be positive. So that means from negative infinity to 1, it's increasing. The graph of the function will be increasing on that interval, negative infinity to 1. Now from 1 to 3, probably the only test value for that will have to be x is equal to 2. And then we'll find out what f prime of 2 is by substituting every x in the f prime of x function. So in this case here, put this out. Let's see, there'll be 3 and then times 2, that's squared, minus 12 times 2 plus 9. That gave me a negative 3, but in this case, at f prime of 2, that's going to be negative. So between 1 and 3, the graph of the function will be decreasing. Okay, and then from 3 to infinity, test value for that would be, let's say, x equals 4. And substitute every x with 4 in that f prime of x function. Now here I'm just going to go back. What I did was second and enter to pull this back up. And I'm just going to replace every 2 that I have here with a 4. And then hit enter. And as you can see here, f prime of 4 came out to be 9, which is positive, so that means that the graph of the function will be increasing. So as you can see here, the graph of this function is increasing on 2 different intervals here. One of them is from negative infinity to 1, and also from 3 to infinity. And also you can see that it's decreasing only on the interval from 1 to 3. Okay. So those are parts E and F done together. All right, questions on part E and F. Now part G is asking on what intervals are the function concave up and then concave down. That's G and H together. Okay, so in this case here, let me pull this page up. Concave up, and then H will be concave down. Okay, also we can do a number line as well. Now we were told our possible inflection point or inflection points was at x is equal to 2. So we'll use the 2 there. And then our interval will be from negative infinity to 2 on the left, and then from 2 to infinity on the right. And f double prime of x was 6x minus 12, by the way, from part B. So we're going to be using that to help us determine concavity. For negative infinity to 2, a good test value for that would be x equals 0. So f double prime of 0, and f double prime of x was 6x minus 12, so we replace the x with 0. So this would be 6 times 0 minus 12, which ends up being negative 12. And that, of course, is negative, so that means the graph will be concave up or down. If it's negative, it's got to be concave down. And then from 2 to infinity, let's test x equals 3. And replace the x with the 3 in the f double prime of x function. So f double prime of 3 will be 6 times 3 minus 12. And this is 18 minus 12. That ends up being 6, which is a positive value. So that means from 2 to infinity, the graph will be concave, up or down? Up. Okay. So, to answer the questions in parts G and H, the graph is concave up from 2 to infinity, and then concave down from negative infinity to 2. Okay. All right. Any questions? Now, I and J deals with the local extrema. I asks for the local maximum. And here I just want the x value where it is a local maximum. So, what x value represents a local maximum? X equals 1. Because we're increasing, and then we're turning around and decreasing. Increasing and then decreasing. So at x equals 1 is your local maximum. And then J as for the local minimum. What x value represents your local minimum? X equals 3. Because as you can see here, on the left of 3, we're decreasing, and then on the right of 3, we're increasing. So your local minimum will be at x equals 3. And that's problem number 3 altogether. All right, are there any questions on problem number 3? Okay. Problem number 4 deals with, number 4 deals with Rolle's theorem. All right, and in this case, we're looking for we're going to determine whether Rolle's theorem applies to the function f of x equals to x cubed minus 3x squared minus 9x minus 5 on the interval from -1 to 5. And if so, find the points that are guaranteed to exist by Rolle's theorem. So there are 3 things that we need to ask ourselves for that particular function. So in this case here, number 4, we got f of x is equal to x cubed minus 3x squared minus 9x minus 5. We need to ask ourselves this question: is the function f continuous on the interval in which is given to us as -1, 5? Is it continuous on that closed interval? And by looking at this, this is a polynomial function. And with a polynomial function, there are no restrictions here. That means that the function is continuous everywhere, and if it's continuous everywhere, it must be continuous on that closed interval, -1, 5. So we can just answer yes for that. Then the next question, is f differentiable on the open interval -1, 5? Well, let's take the derivative of that function. In this case here, what's f prime of x going to be? What would be f prime of x for this function? 3x what?
Squared.
Squared. Minus,
6x minus 9.
okay, there we go. It is differentiable, and it is still a polynomial function, okay, because there are no restrictions here on that f prime of x. So we can say that the open interval negative 1, 5 is differentiable. Well, the function f prime of x is differentiable on that open interval. And then the next question is this: does f of a equal f of b? So that means we need to evaluate our endpoints on this closed interval. Here a is going to be 1 and negative 1 and b is 5. So f of a, or f of negative 1, we just substitute every x in the original function with negative 1. So this would be negative 1 cubed minus 3 times negative 1, and that's squared, minus 9 times negative 1, minus 5. So in this case here, negative 1, and then that's cube, minus 3 times negative 1, and that's squared, minus 9 times negative 1, minus 5. Here we get 0. So that means when I do f of b, or f of 5, I must also get 0 as well. So here I'm going to have 5 cubed minus 3 times 5, and that's squared, minus 9 times 5, minus 5. So here I'm going to have 5 cubed minus 3 times 5 squared. Actually, delete. To delete that. Close parentheses and then squared. Minus 9 times 5, minus 5. That also equals 0. So f of a does equal to f of b. So that means that Rolle's theorem applies, because all three conditions are met. All right, and we're going to find a point or points that are guaranteed to exist by Rolle's theorem. That means we take that f prime of x, set that equal to 0. And f prime of x was that 3x squared minus 6x minus 9. That's going to be set equal to 0. Okay, what can we factor out in 3x squared minus 6x minus 9?
3.
Let's factor out the 3. So that means we'll have x squared minus 2x minus 3 equal to 0. And let's see, we can factor x squared minus 2x minus 3. X squared breaks up as x and x. What factors over minus 3 gives me minus 2x as a middle term?
Minus 3 and plus 1.
Plus 1. So I get 3 times x minus 3 times x plus 1 equal to 0. And then we set each factor equal to 0. So I'm going to set 3 equal to 0, x minus 3 equals 0, and x plus 1 equal to 0. Well, 3 is equal to 0. I can eliminate that. For x minus 3 equal to 0, that means x is equal to 3. And for x plus 1 equals 0, x must be equal to negative 1. All right, now, is 3 in the interval, in the open interval from -1 to 5? Yes.
Um,
Yes or no? Yeah. What about -1?
No.
It's not. So we need to eliminate x equal -1 because that's not in the open interval. So the only point that is guaranteed to exist will have to be x equals 3. So we can say here that the point that is guaranteed to exist by Rolle's theorem is, and I'm just going to say x equals 3. Are there any questions about problem number 4? Okay, problem number 5. Determine whether the mean value theorem applies to the function f of x is equal to e to the x on the interval from 0 to the natural log of 4. Okay. And if so, find the points that are guaranteed to exist by the mean value theorem. So with that, there's only 2 questions that we have to ask ourselves. Is the function continuous on the closed interval? And is it differentiable on the open interval? And if that's the case, then the mean value theorem applies. So here, f of x is equal to, let's see, e to the x. The interval is from 0 to the natural log of 4. So that means, let's ask ourselves this question. Is f continuous on the closed intervals 0 to ln of 4? Well, the graph of f of x equals e to the x. Okay, we do have a value for e of 0 and e of ln of 4, and it's continuous pretty much from 0 on up to infinity, by the way. So, to answer that question, it would be yes. And is the function differentiable on the open interval? Well, what's the derivative of e to the x? Of course, e to the x, that's the simplest derivative to take. So f prime of x is also e to the x. So pretty much it's going to be continuous pretty much everywhere from negative infinity to infinity. So I'll say yes for that one. Okay. So now, since both conditions are met, we can say that the mean value theorem applies. Or can be applied. So now we need to find the points that are guaranteed to exist by the mean value theorem. All right, so let's first find out what f of a is and what f of b is. Now that f of a, here is going to be f of 0. And here f of x is e to the x, so e to the 0 would be what?
1.
Just 1. And then for f of b, b is ln of 4, so let's evaluate f of ln of 4. So it'd be e to the ln of 4. And what's e to the ln of 4?
4.
Just 4. That's one of those inverse properties for natural logarithms. E to the ln of whatever is whatever. Because e and ln are inverses of each other. Okay. So now we're going to use that mean value theorem where you have f of b minus f of a, and that's divided by b minus a, equals f prime of some constant c. All right, in this case, f of b, we found that out to be 4, minus f of a, we found that out to be 1. That's over b minus a. Here's a, and that's b. b is ln of 4 minus a, which is 0. And that's equal to, well, f prime of x was e to the x, so f prime of c would just be e to the power of c. And then when I do 4 minus 1, that's going to be 3. So I have 3 over ln of 4 minus 0 will just be ln of 4. So 3 over ln of 4 would be equal to e to the power of c. Now I need to solve this for c. Since e and ln are inverses of each other, I'm going to take the natural log on both sides. So on the right side, ln of e to whatever my exponent is that exponent. So ln of e to the c would just be c. And then that's just going to be equal to ln of 3 divided by the natural log of 4. And I would go no further than that. Okay. So this represents the point that is guaranteed to exist. By the mean value theorem. Okay. Now both problems 4 and 5 are from section 4.2. All right. Any questions on problem number 5? Bless you. All right, problem number 6 is an optimization problem. And this one is similar to an example that I did out of that section. And that is a rectangular flower with an area of 170 square meters is surrounded by a grass border 1 meter wide on 2 sides and a 2 meters wide on the other 2 sides as shown in this figure. What dimensions of the garden minimize the combined area of the garden and the borders? Okay, so in this case here, so this right here represents the area of the flower garden, 170. And that's in square meters, by the way. All right. And there's 2 meters on this side and also 2 meters on this side as well. There's 1 meter this way, and this way right here is also 1 meter. And of course, the area, of course, of a rectangle is going to be length times the width. Length times the width. And we're told that the area of the garden is 170 square meters. So I know something about this. The width times the height. And I'm using W for the width and the H for the height. That's 170. So if this is going to be the width going in this direction, and this is the height going in this direction up and down, then the total width would have to be this, the W, and then I got 2 on the left and 2 on the right. So it'd be W plus 4. And then going in this direction, if this is the height, and I got 1 meter and 1 meter, well, 1 plus 1 is 2, so this whole height altogether will be H plus 2. So the area of the garden and the borders itself would be W plus 4 times H plus 2. So here's what I'm going to have. A is equal to W plus 4 times H plus 2. Okay, here it is. This is the width of the garden, going from left to right. That's W. I got 2 on the left and 2 on the right. 2 plus 2, that's 4. That's where the W plus 4 comes from. Any other questions? Okay. Now here's what I'm going to do here. I want this equation in terms of H. That means I need to solve for this W times the width times the height, W times H equals 170. I need to solve for W. And to do that, I need to divide both sides by H. So that means W is equal to 170 divided by H. Okay. Now I'm going to take the 170 over H and substitute it for this W in this objective formula. So here's what I'm going to have. A is equal to W, which is 170 over H, plus 4, times the quantity H plus 2. Yes.
Why is it 4 and 2 when the area is oh, yeah, I see.
Okay.
Right.
Okay. Any other questions? All right, so now let's use the form method because we need to multiply this out. All right, think about this. When you have 170 over H times H, that H is like H over 1, your H's will divide out. You'll be left with 170. Then the outer would be 170 over H times 2. Well, that 2 is going to be 2 over 1, so 170 over H times 2 over 1 would be up plus 340 over H. Then the inner will be 4 times H will be 4H. And then the last times the last, 4 times 2 would be 8. Okay. So now let's combine some like terms here. 170 plus 8 will be 178. And I'm going to pull the h out of the denominator and write this as 340 times h to the negative 1 plus 4h. And then I'm going to take the derivative of that function. So when I do that, the derivative of this, the derivative of 178 is 0. For 340, h to the negative 1, its derivative will be this. Bring the negative sign, that'll be minus 340. Copy the h over to the 1 less power. Negative 1 minus 1 would be negative 2. Plus the derivative of 4h will be 4. And I can also write this as negative 340 divided by h squared. And then plus 4. And I'll set a prime to be equal to 0. So that means I'm going to have negative 340 over h squared plus 4 is equal to 0. And since I got that h squared in the denominator, I'm going to multiply both sides of this equation by h squared. So h squared would be multiplied by that negative 340 over h squared plus 4 equal to h squared will be multiplied by 0. When I do that, h squared times negative 340 over h squared will be negative 340 plus h squared times the 4 will be 4h squared. That's equal to 0. And now when I add 340 to both sides, so we got 4h squared is equal to 340. And then divide by 4, h squared will be equal to what? 340 divided by 4. Should get 85. And then, of course, the opposite of squaring something would be to take its square root. Now, I'm not going to deal with that plus or minus because we know that measurements can't be negative. So it'll be h is equal to, and I'll leave this as the square root of 85. Okay. And in this case, we're trying to minimize the combined area, so that means h being the square root of 85, that would be your local minimum. And now to find out what the width is, if you recall, I let the width be equal to 170 over h. When we had width times height equal to 170, and we divided by h to solve for w. So now I can go ahead and substitute the h with the square root of 85, so it'll be 170 over the square root of 85. And of course, to rationalize the denominator, we multiply the numerator and the denominator by the square root of 85. Square root of 85 times itself will give me the 85. And then if I divide 85 into 170, that'll go 2 times. So this will be 2 square roots of 85. And this is in meters. Just like our height is going to be in meters as well. Bring that up. So the dimensions of that garden would be square root of 85 meters by 2 square root of 85. meters. All right. Are there any questions about problem number 6? Okay, problem number 7 deals with linear approximation, which is section 4.6. All right, so here we're going to choose a value that produces a small error and estimate the following quantities, like the square root of 146. All right, in this case here, we're dealing with the square root, so we need the largest perfect square that is less than 146. And that's going to be what? Yeah, 12 times 12, which is 144. So I'm going to let A be 144. And of course, that would mean f of x would be the square root of x. And by the way, what's f prime of x going to be? What's f prime of x? What's the derivative of the square root of x? 1 over 2 square root of x. Okay. So, let's see here. If I'm letting a be 144, then f of a, which will be f of 144, that's going to be equal to the square root of x, which is 144. A, which is 144. And of course, that's going to be 12. And then f prime of a, that's f prime of 144. And f prime of x is 1 over 2 square root of x. So it'll be 1 over 2 square root of 144. Which will be 1 over 2 times, well, square root of 144, that's 12. And 2 times 12 would give us 24. So f prime at 144 would be 1 over 24. And then our linear approximation function is this. L of x is equal to f of a plus f prime of a times the quantity x minus a. So here f of a, we found that out to be 12, plus f prime of a, that was 1 over 24, times x, which is, this is your x right here, 146. Minus a is equal to 144. Okay. And I forgot to mention that x was going to be equal to 146. So in this case here, this will be 12 plus 1 over 24 times 146 minus 144, that's 2. And I can do this in the calculator. So this would be 12 plus, and in parentheses, 1 divided by 24, close parentheses, times 2. Now let's say the 3 decimal places, this will be approximately 12.083. So this represents the approximate value for the square root of 146. Okay. Any questions about part A? Part B is, let's say we had e to the 0.06. Okay, so if I let x equals to that exponent of 0.06, then that means my f of x will be e to the x. And what's f prime of x?
E to the x.
E to the x. Okay. So now, we need to choose a to be some number that we can easily find out what e to the x is.
E to the 0.
E to the 0. So if I let a be 0, then that means here f of a, or f of 0, that's e to the 0, which is 1. And the same holds true for f prime of a, which is f prime of 0. And again, e to the 0 is 1. Now, of course, L of x would be f of a plus f prime of a times the quantity x minus a. Well, f of a, that's 1, plus f prime of a, that's also 1, times x minus a. Well, x is 0.06 minus a, which was, we chose that to be 0. And if I multiply all this out, put that in the calculator, that would be 0.06. I mean 1.06. Because that's 1 plus 1 times 0.06. So it's 1.06 for the final answer. That would be your linear approximation for e to the 0.06 power. Questions on number 7. All right, number 8. Say I want to evaluate the following limits. No, take that back. These are differentials also in section 4.6. Consider the following functions and express the relationship between a small change in x and the corresponding change in y in the form dy is equal to f prime of x dx. So in part A, we got this. Why do I not have this as f of x equals to 3x cubed minus 4x? Each one of them should have f of x in front of them. Okay. So f prime of x, what would f prime of x be?
9x squared minus 4.
9x squared minus 4. And then we write that in the form of dy is equal to f prime of x dx. So we just bring down the dy, and that's equal to f prime of x, that's just 9x squared minus 4. I'm putting that in parentheses, dx. That's all there is to it. So these should not be a problem. And then part B is the ln of 1 minus x. Or I should say f of x is equal to ln of 1 minus x. All right, so now what's f prime of x going to be?
1 over 1 minus x
Okay, 1 over 1 minus x times something else,
times 1. Times negative 1.
times negative 1. Because you got to use the chain rule on that one. All right, so if I simplify this, this should just be negative 1 over 1 minus x for f prime of x. And then, of course, we write that in the form of a differential, dy is equal to f prime of x dx. So dy would be that part right there, the 1, negative 1, over 1 minus x dx. And that's all there is to it. Are there any questions about problem number 8? Okay, problem number 9 deals with L'Hopital's rule. So here we've got the limit as x approaches -1 of x to the fourth plus x cubed plus 2x plus 2, all divided by x plus 1. Okay, now, if I was to use direct substitution, what's going to happen here is, here I would get a 0 in the numerator and a 0 in the denominator. I'm going to get an indeterminate form, 0 over 0. So what that means here is this: I need to take the derivative of the numerator and the derivative of the denominator until I don't get that indeterminate form. So if I take the derivative of x to the fourth plus x cubed plus 2x squared plus 2, I'm still going to bring this limit as x approaches -1. This derivative of x to the fourth would be 4x cubed plus derivative of x cubed would be 3x squared. The derivative of 2x will be 2, and the derivative of 2 is 0. The derivative of x plus 1 ends up being 1. So now I no longer have the 0 over the 0 indeterminate form, which means I can go in and use direct substitution by replacing every x with -1. Well, I'm cubing. A negative to an odd power would be negative, so -1 cubed would be -1 times the 4 would be -4. Square negative is going to be positive, so -1 squared would be 1 times 3 would be 3. And if I do -4 plus 3, that's -1 plus 2 is 1. So the limit as x approaches -1 of x to the fourth plus x cubed plus 2x plus 2 divided by x plus 1 using L'Hopital's rule will be 1. Questions on part A. Okay, part B is going to be the limit as x approaches 0 of e to the x minus 1 divided by 5x squared. Well, in the numerator, I will get 0. The denominator, I'll get 0, so I have the indeterminate form, 0 over 0. Okay, so let's go ahead and take the derivative of the numerator and the derivative of the denominator. Well, the derivative of e to the x will be e to the x. The derivative minus the derivative of x is 1, divided by the derivative of 5x squared, 10x. Now notice I'm still going to have that indeterminate form because replacing the x with 0, this will be e to the 0, which is 1 minus 1, that's 0. 10 times 0 is 0, so I have 0 over 0 again. So now I have to use the L'Hopital's rule again. Let's take the derivative of e to the x minus 1, which is e to the x. And the derivative of 10x will be just 10. So I no longer have that 0 over 0 indeterminate form. I can go ahead and replace the x with 0, so this would be e to the 0 divided by 10. And e to the 0 is 1 over 10. So that's the limit as x approaches 0 of e to the x minus 1 divided by 5x squared. And that's 1/10. So sometimes you may have to use L'Hopital's rule multiple times.
So how do we have 0 over 0 again? Right
If you try to use direct substitution, like in this case right here, if I replace this x with 0, that's e to the 0, which is 1, minus 1, that's 0 in the numerator. The denominator, 10 times 0 is 0. So 0 over 0, that's the indeterminate form. That tells you you need to use L'Hopital's rule. Any other questions? All right, part C is the limit as x approaches infinity. of 4x cubed minus 2x squared plus 6 divided by pi x squared, x cubed, pi x cubed plus 4. So in this case, I guess we'll have to use L'Hopital's rule multiple times, because now we have another type of indeterminate form, infinity over infinity. So the derivative of 4x cubed would be 12x squared minus derivative of 2x squared would be 4, minus 4x. And then the derivative of pi x cubed. Bring this 3 down, it'll be 3 pi, then the x will be squared. Well, I still got infinity over infinity.
What a x.
That should be infinity. Okay. I've been used to putting x approaching 0. Okay. Now, let's use L'Hopital's rule again. The derivative of 12x squared would be 24x minus the derivative of 4x, 4. That's going to be divided by the derivative of 3x squared. Bring this 2 down, multiplied by the 3, you'll get 6 pi x. And again, I'm still getting infinity over infinity. So again, we'll use L'Hopital's rule. The derivative of 24x will be 24, and then the derivative of 6 pi x will be 6 pi. Well, guess what? We have constants in the numerator and the denominator. So that means that the limit of a constant is a constant. So it'll just be 24 over 6 pi, but I can reduce by dividing 6 into 24, which will go 4 times. So I have 4 over pi. And that will be it right there. That's the limit as x approaches infinity of 4x cubed minus 2x squared plus 6 divided by pi x cubed plus 4. Okay. Any questions about part C? And finally, part D. Notice I'm using trig functions here. The limit as x approaches 0 of the cosecant of 6x times the sine of 7x. With that problem, I know something about this. The cosecant, as you let x approach 0, that's going to go to infinity, and I know the sine of 0 is 0, so I got an infinity times 0 situation. What I need to do here is write this in a different way, so I will have either 0 over 0 as an indeterminate form, or negative infinity, or infinity over infinity as the indeterminate form. So let me bring up the limit as x approaches 0. Using a trig identity, the cosecant of 6 over x, that's going to be, and I know what this is, 1 over the sine of 6x. That's one of those trig identities or reciprocal identities that we talked about way back in section 1.4. And that's multiplied by the sine of 7x. So here's where I'm going to have the limit as x approaches 0 of the sine of 7x divided by the sine of 6x. Well, I know sine of 0 is 0, and sine in the same holds true in the denominator. So I have 0 over 0, which I can use L'Hopital's rule. So I need to bring down the limit as x approaches 0. If I take the derivative of sine of 7x, I will have what? Cosine of 7x times what? 7. Have to use the chain rule. What about the derivative of the sine of 6x?
6 cosine of 6x.
6 times the cosine of 6x. All right, now I can go ahead and do direct substitution here. Let me put this underneath it. Have 7 times the cosine of, well, what's 7 times 0? 0. And then 6 times the cosine of 6 times 0, that's also 0. What's the cosine of 0? 1. So this will be 7 times 1 divided by 6 times 1. That's going to end up being 7 over 6. So that will be the limit as x approaches 0 of the cosecant of 6x times the sine of 7x. That's going to end up being 7 over 6. So sometimes you have to, use those trig identities back in section 1.4. Any questions about part D? Or any questions about problem number 9? Or any questions about what's going to be on exam number 4?